We are very pleased that we have a very interesting panel prepared for you today with the help of Chris Sallerberger, the chairman of the IEF Exploration Committee. And I would like to ask Chris to come on stage and start the panel, introducing the panelists and introducing the topic with the title Unlocking the Mysteries of Our Solar System, Recent Developments from the Dawn, Hayabusa and Rosetta mission. Please enjoy.
Thank you, Christian. If I could ask the panelists, please, to come up and have a seat. You know, as you said, a change of topic and in some ways difficult to follow that very touching set of presentations that we just had on Hans Hofmann. You know, we all knew him well in this community, and he was certainly very well passionate about space. And I think this next topic is one that he would have been very enthusiastic about as well. So perhaps not as disjointed as one might think. So we've assembled a panel here. Okay, that's okay. I guess we'll work out the presentations. So this panel is on unlocking the mysteries of our solar system. Recent developments from the Dawn, Hayabusa 2, and Rosetta missions. As you know, space programs around the world today are engaged in unlocking some of the mysteries of our solar system. And we're doing this by sending robotic spacecraft out there to really understand those small bodies and the insights they bring to our solar system. So we have the Dawn mission, the NASA's Dawn mission, which is currently out there in the asteroid belt. It's visited the asteroid Vesta with some very exciting results, and just this month has arrived at its second target, the dwarf planet Ceres, and is preparing to do some very exciting things there that we'll hear about. Also, just this past December, JAXA launched the Hayabusa 2 mission, which will explore an asteroid, but even more than that, will return samples from that asteroid to the Earth. Very exciting thing. And then the third mission that we'll be hearing about tonight is the Rosetta mission. Of course, we've all heard about it already. It kind of bookended the Congress that we had last autumn. Just before it, in August, the Rosetta mission arrived at its target comet, and then in November, just a few weeks after our Congress, it deployed the Philae lander to the surface, and we all remember the excitement about that. So we'll have some further insight shared into those three missions. So we, with that introduction, I think we're ready technically as well. That's good. Let me introduce the panelists, and the way we'll run this, we'll have some brief presentations, perhaps 15 or 20-minute presentations from each of the panelists on those missions, and then we'll engage in a bit of a discussion as much as we have time, and have opportunity also from questions from the audience to be answered. So I begin with, in fact, let me introduce the panelists as we go, and I won't spend too much time because I know we have very exciting presentations. The first will be James Graff. Jim works at JPL. He's one of the senior management of JPL, has been involved in a number of deep space missions over the years, and I'll turn it over to Jim to talk to us about the Dawn mission.
Excuse me? The remote, okay, the remote. Thank you, Chris. Okay, can we have the introduction view graph, please? No, the first one.
You need this remote here.
No, I have one here. Thank you. I think you even have a pointer. Okay, I'm James Graff, as Chris said, and I'm representing Mark Raymond, who's the project manager for Dawn. And you will see there's a number of organizations that have supported this mission. First couple on the left are from the United States, and the others are from across the pond over in Europe. And I'll talk about them in just a little bit when I get to the instrument itself. The one that's not on here, though, it's important, and all of us use, and doesn't get enough acknowledgement, is the Deep Space Network. We don't leave home, Earth home, without it. So that's one that's provided a tremendous capability to all the missions that you're going to hear about. So let me move on. I'm going to briefly describe a little bit of the trajectory. We left Earth in September of 07. We had a flyby, very rapid flyby of Mars about a year and a half later. Took us about 2.5 years to get into Vesta, and then we spent there about 18 months at Vesta. Then we went on again for another 2.5 years and got to Ceres. We just had essentially capture on March 6th of this month. The things that they are actually working on is looking and mapping the surface in color, and at the same time developing a topography of the individual asteroids and dwarf planet. They're also looking at the elemental composition, the mineralogy of it, looking for moons, and also trying to measure the gravity of the various bodies that they've gone ahead and met. Now, I've given you this one to point out a couple of quick things. We're not just talking about going to an asteroid and a dwarf planet. We're actually talking about a major use of electric propulsion. And many of us that are used to chemical propulsion are not, in fact, in tune with what it means when you have a constant low thrust that is provided by electric propulsion. In this one, you can see, obviously, do we have a pointer here? Is there a pointer with this?
You're looking for a laser pointer?
A laser pointer. Is there one? Okay. Just to show that we left Earth, and then we had the Mars flyby, and then we were thrusting most of the way out to Vesta. Thank you. Most of the way out to Vesta. When you get to Vesta, you're not flying by Vesta here. You're actually going deep into the gravitational well. You're going to circle it, go down into the well, and then you come back out of the well when you're finished, and then you move on to Ceres, and you do the same thing there. So it's not a flyby that we're used to seeing here. We were with Vesta for about a quarter of an orbit, and then we went on to Ceres. And what you're doing is matching the heliocentric velocity, really, of the individual body. You're not flying by it quickly. So, just to go back one other if we can. What you're seeing here in the blue represents their actual thrusting. And the red means that they actually stopped thrusting. They've turned the spacecraft to communicating back to Earth. So again, you're under constant thrust for a great period of the time during the trajectory from one body to another. Just to give you a sense of the size, Ceres is 950 kilometers in diameter, and you can see how big Vesta is here. You can also get a sense of some other bodies that you might know about. That's Pluto and the Earth's moon. Now, this is about Ceres and about the electric propulsion to get us there, but I figured I had to show a little bit about Vesta. This is one image that we have taken from Vesta. There's lots of them, and I have them in the backup, but this is the one I selected just to show you the rocky surface, the dusty surface of Vesta when it got there. And so that's what an asteroid will look like. And then we can go on and talk about the ion thrusting itself. This is, again, a very unique aspect of this mission. Dawn has actually had about the greatest delta V of any mission that we know about to date. It's also had the longest powered flight. So the delta V that's actually been accumulated to this day, today, is about 10.7 kilometers per second out of the one ion engine that they've been using. They actually have 3 on board. At the same time, that's about equivalent. At the end of the mission, they will have used up about 11 kilometers per second, and that's about equivalent to what the Delta V, the Delta II was that actually put them in orbit. So it's really quite a lot of delta V that they're getting from this rather novel propulsion system. A couple other things, the powered flight is about 5.2 years, and you can see how far it's been since the Big Bang there too. And lastly, we will probably have been thrusting for about 5.5 years by the time we get to the end of the mission. Now, I said I'd talk a little bit about the contributions from the Europeans, and that comes in the form of the science instruments themselves. They have on board a redundant framing camera that comes from the Max Planck Institute and from DLR, and that's shown over here on the left. There's actually two of them. In the center is the visible and near-infrared mapping spectrometers, which come from the Italian Space Agency and the Italian Institute for Astrophysics. And lastly, we have the gamma ray and neutron spectrometers that come from Los Alamos in the United States and operated by the Planetary Science Institute. So before we got the series, this was the best image that we knew about. It came from Hubble Space Telescope. What you can see are some of the white spots that come in here, which are tantalizing, but what they are, no one could really tell. Ceres is the only dwarf planet that we have right now that exists in the inner solar system. It's the largest body that's in the asteroid belt. It contains about 30% of the mass of the asteroid belt itself. As I said, it's about 950 kilometers in diameter, to give you a sense. And I think there's one notable point to make from this view graph, and that is that the Herschel Space Observatory actually did find tenuous water vapor when they took their telescope and they looked back at it about 18 months ago, maybe 12 months ago. That is very tantalizing. That with the geysers that we've seen on Enceladus makes you start wondering, well, what is happening here at the planet? And that, at this particular point, they do not know. What else did they know about Ceres up to this point is they knew that it had a thin, dusty crust. They believed there was water ice underneath that, and then it was a rocky core. And so what they're going to do is, of course, map the surface properties. They're going to try to probe the interior and understand the relationship. Now, I mentioned electric propulsion. The green line represents when they're actually thrusting towards the Ceres, the body itself, which is located right over here in this area. So you're actually thrusting towards it. You're actually catching up to the body, and you actually turn and then start slowing down and then coming back to be captured in orbit. A couple of images that it's not coming out. No, that doesn't come across, I'm sorry. See if this will work. This is an animation of, if it comes up, of Ceres. You're looking beyond Ceres, looking back. Can you see it? Is it coming up, or is it? No? Okay. Oh, here it comes. On the left is the actual spacecraft, and on the right is Ceres itself. And you're seeing we're coming over the North Pole and off to the side. We're actually thrusting and slowing ourselves down. We make a 180-degree turn. We change our angular momentum vector and then start again in towards the North Pole. Then we start thrusting in the opposite direction to slow ourselves down and to go into our original polar orbit. All the orbits that we're going to be using will be circular and polar while we stay there for about 18 months investigating the planet. Now, if we turn this around, it gives you a sense of what electric propulsion, how it changes your approach to orbit insertion. There is no critical event here. There's no intensive fault protection. We've got to make sure it happens. You know, if we went into safe mode, all we do is slow ourselves down a little bit more, a little later, and come back. So it really changes your whole attitude towards the design of the mission and of the spacecraft. A couple of things on the orbits themselves. The first orbit we'll go into, it'll be 13,500 kilometers. It is a very high orbit. in here, we're going to be doing a couple of science activities. One, we'll be looking for satellites. Two, we'll be going ahead and observing at a high phase angle from the rear, looking for any jets that we might be able to see along the limb in case it's possible. Remember, though, that this mission was conceived back in the early 2000s, and at that time, we didn't know anything about geysers. We didn't know anything about the emissions of water vapor, and so the instruments themselves, the whole mission has really been designed to look at a solid body, not to look at the rather ephemeral geysers that come along. So we'll be looking at, again, at the planet. We'll characterize the rotational rate here. Then we will spend about another month slowing ourselves down and coming to an orbit that's about 4,400 kilometers, and we'll start doing some intensive science on the sunlit side. When we get to the night side, we'll be relaying all the data back to Earth. Then we got one more. We'll come down to two more orbits. When we get down to the lower orbit, which is 1,470 kilometers, that will be where we do most of the imaging on the sunlit side with the framing camera and the mapping spectrometer. And at the same time, we'll start really getting better gravity fields that will set ourselves up for later. Last orbit will be about 375 kilometers. When we get down to that level, that's when the gamma ray and the neutron spectrometer and the gravity science will come into play. And you can see the dates in here. We start in March, and we arrive at this inner orbit in December. We'll be operating until March of 16, returning critical data until that point. This is some images of Sirius that they took on approach, and it's the same scale up above and down below, about 200 kilometers shown here. Just to give you a sense of what you're looking at is these are what they call the Great White Spot. They observed it. Obviously, we observed it at Herschel, and now we're seeing it close up. It's not one spot, it's two spots, and it's in a crater that's about 90 kilometers wide. There are a bunch of other white spots that we've noticed here. Whether this is ejecta from a meteorite hit, or whether it's cryovolcanism that's resulting in salt on the surface, we can't tell at this particular point in time. That remains to be seen as we start unfolding this mystery. A couple other things to look for. Over here is a polygonal shape with not many craters, and we don't really understand what's causing that. And there are a bunch of cliffs and looks like some sort of rills that are created there. So it's a very intriguing dwarf planet, and we'll be unfolding the science associated with it as we go forward. So lastly, I'll just say that we have searched for moons. We've not seen moons to date, and that will continue in April. We'll search for water vapor when we're in the high phase angle, the very first orbit. That'll be the only time we'll have a chance and an opportunity to really see that, partly because the instruments weren't designed for it, and partly because the dwarf planet's at aphelion and it's not very active right now. The stereo mapping will take place from August to October, and we expect to accomplish all the mission objectives by March of 16. We do, in the final orbit, the 375 kilometers, that keeps us stable, so we will not crash into the dwarf planet for at least 50 years. That's a planetary protection requirement that we have to agree to. So with that in mind, that's the end of my talk. Thank you.
Thanks so much, Jim. A fascinating talk. I'm sure there are a number of questions. I have a few myself, but we'll hold until all the presentations are done, and then we'll ask some questions and maybe have some discussion between the panelists. So next presentation will be on the Hayabusa 2 mission, and the presentation will be given by Professor Hitoshi Kuninaka, who works for JAXA. He is the Hayabusa 2 project manager. So, please.
Thank you very much. can I get? So thank you very much. So it's my great honor to have an opportunity to present our space activity. My name is Hitoshi Kuninaka, project manager of Hayabusa 2. So first pages show you the remember of Hayabusa 1. So we have already launched the spacecraft Hayabusa Asteroid Explorer. It was launched in 2003, and then and then finally, original plan Hayabusa came back to us again 2007. But in the space operation, we have a lot of the troubles, and then so in order to solve these problems, we prolong the mission of the Hayabusa, and finally, spacecraft come back to Earth 2010. And then this is an image of the asteroid Itokawa, Hayabusa, that is taken by Hayabusa Asteroid Explorer. That is a C-type asteroid. So tip-to-tip length is about 500 meters. So very strange shape of the asteroid. And then so on this surface, we executed the successful landing operation on the surface of the Itokawa. At that moment, we collect the surface material from the surface. And then you can see the shadow of the Hayabusa itself projected on the surface of the Itokawa. And then so final operation, we executed the recovery operation at the Umera Desert. So original plan, once the re-entry vehicle was separated from the main spacecraft, so Hayabusa take escape maneuver. But on the way of the space mission, we lost of the function of reaction hydrogen thruster capability, so that the unique way is the delta V unique way is only by ion engine system. So that we decided to the whole of the spacecraft dive into the Earth atmosphere. So light luminosity means the explosion of the whole of the spacecraft. But you can see the small bright spot. That is the flight of the re-entry vehicle. And then so 2010, June 13th, we succeeded the recovery operation of the re-entry vehicle at the Umera Desert. And based on the achievement of the Hayabusa 1, so Hayabusa 1 is the technological demonstrator, precursor demonstrator for the asteroid sample return mission. And the achievement of the Hayabusa 1 mission, we started to develop the Hayabusa 2. So next mission is the scientific space mission. The next target is the 1990 JU3. So it is the C-type asteroid. So previous target Itokawa is classified to the S-type, stone-type asteroid, but the next target is a C-type, carbonaceous chondrite. So scientists expected to reveal the water or an organic material from the asteroid. And then so in order to execute the scientific mission, we developed we improved the space technology. For example, the original Hayabusa, we installed the 3 reaction wheel system. But in order to make a robust system, we installed the 4 reaction wheel system. And as for the ion engine, original ion engine generates only 8 millinewton thrust force. But we succeeded to develop to enhance the thrust force 8 millinewton to 10 millinewton. And we installed the 4 ion engine system. And this page shows you the onboard instrument. So we select the various kind of the remote sensing devices, focusing on the science. So these devices are tuned to the C-type asteroid. They are optical navigation camera, light detection and lensing LiDAR, and near-infrared spectrometer, and a thermal imager, so on. Another approach is the small landing and the rovers. So we install the 4 landing system, 3 Minervas and 1 mascot. So Minerva was developed by JAXA and Japanese university people. And another one, a mascot, is delivered from the DLR and the CNES. And so this device will take a close-up data on the surface of the asteroid. And then so that combine the previous remote sensing device so that we can get the scientific data, large diversity, so 3-dimensional data, so remote, including the remote sensing and close-up data. And another development, another engineering challenge, we developed the small carrion impactor. That is a very, very small one. Diameter is about 30 centimeter, and the total weight is about 20 kilogram, including the gunpowder and copper projectile. And then so next movie, I can show you the, how can I turn off this? Excuse me.
Where's the arrow? Could you help with the, just what is it you're looking, just click.
どうやったら止められる？あ、これかな。How can I finish this PowerPoint? Escape. Okay, I see. Thank you. And then so, これはどうかな。
To drag the movie onto the other screen. It's just this one.
Yes.
And then is that the maximize button? It is. And now should be running. There you go.
This is the real scale experiment on the ground. Just like it, so a small projectile is ejected to the downstream, and soれでこれか。どうやったらできるんだろう。Yes, yeah, I want to use another movie. I'm
Show
sorry.
another movie.
Another movie, this
Same
one.
thing.
Thank you. So 100 meter downstream, we have a sun target, so that the projectile shoots the sun target. So that's a very straightforward capability. So that once we separate the projectile from the impactor from the spacecraft, so projectile penetrates the surface of the asteroid. And then so using this device, so I went to the following the space maneuver, space operation. Please select the,
Presentation.
yes.
Oh, another
so
movie.
yeah, this one. Next one. No. Yeah, that's one.
It'll be slow. It'll take a while, but it'll come. There we go. So we need to exit that one. get out of that movie now? I'm blind without my glasses on. Ta-da. Hold on. Now I need to get out of that movie. There we go. And go into this one.
Thanks, Alex. So this is a computer graphic for the proximity operation around the asteroid. So first, spacecraft achieved to the rendezvous to the target asteroid, and then first of all we will execute the remote sensing, and then we try to the surface touchdown. So first, target marker is released, and then spacecraft automatically follow the target marker, and then approach to the surface. And then at that moment, we collect the surface material at that touchdown operation. So this scheme is almost the same to the original Hayabusa 1. And the next one is the impactor operation. So bottom bay impactor was just released. And that, at that moment, spacecraft takes the escape maneuver. And Hayabusa 2 will go to the another side of the asteroid in order to protect the fragment of the released from the impactor. And then we want to make a new crater on the surface of the asteroid. And then after that, the spacecraft come back to the original position. And then we try to touch down the vicinity of the new craters. So this meaning of this operation is we want to get the internal material of the asteroid. Okay, thank you. So that I want to go back to the PowerPoint. Okay, thank you.
To the next one.
Thanks. So that's the combining these technology, we successfully assembled the whole of the spacecraft Hayabusa 2. And then spacecraft was launched to the H2A rocket last year, December. And then after the launch, we executed the commissioning phase. And then that is
all systems are ready.
this is the launch campaign of the H2A rocket number 26.
小型ペイロード3機を搭載した H2A ロケット26号機は平成26年12月3日午後1時22分04秒に種子島宇宙センターから打ち上げられました。
And then this view graph shows you the orbit of the Hayabusa 2. So this is the rotational coordinate system. So Sun and Earth, location of the Sun and Earth are fixed in this figure. So red line means the relative position of the spacecraft. So spacecraft Hayabusa 2 is now located here. And then we have already turned on ion engine. And then spacecraft is on the orbit to come back to Earth again. And then 1 year later, end of this year, spacecraft come back to Earth. And then at that moment, we will execute the Earth by, and the spacecraft was input to the transfer orbit to forward to asteroid. And then 2 years later, spacecraft, 3 years later, spacecraft executed the rendezvous at the target asteroid 1990 J3. And then 1 year and a half, we will execute the proximity operation, and the spacecraft, and then end of 2019, spacecraft leaves the asteroid, and then 1 year later, end of 2020, spacecraft Hayabusa 2 will come back to Earth. So this is the final page. So this is a sequence of event of Hayabusa 2. That is the whole of the explanation of the Hayabusa 2 space mission. That's all. Thank you very much.
ありがとうございます、国中先生. Very interesting mission. A few years ahead still for that mission. I think we'll be following that one like we were following the Dawn mission with Jim and colleagues, as that one was traveling out and then doing its discoveries. We'll be following the Hayabusa 2 mission the same way. So then we move to the some presentations on the last of our 3 missions that we'll be examining tonight. It's the Rosetta mission, and I have here first Mark and then Bernd. Is that the right order? Okay, good. So the next presentation will be given by Mark McCogran, who is the Senior Science Advisor at ESA, and will share with us some of the science aspects of the mission. He's also very good working computers, I noticed.
Great. Well, thank you very much. It's an enormous privilege to be here this evening to talk with our colleagues from Japan and from the US. And of course, on behalf of everybody involved in this amazing mission, Rosetta, not only the European Space Agency and lots of people in there for more than 20 years now, but partners throughout Europe and with the US as well. So it's a true international collaboration, Rosetta, and a true international success. It's a cooperative mission that could not have been done by anybody, I don't think, but that team of people. And I'm very proud to be able to be here to represent the first half, Rosetta, this evening, and Bernd will talk about the Philae landing, of course, which took place on the 12th of November last year. But let me start by motivating why you would want to go to comets in the first place. What's special about a comet? Why is it worth 10 years of a mission to go there? Comets are not only beautiful objects which appear in the sky, the night sky. We're long overdue a spectacular comet in the northern hemisphere. This is Comet McNaught, seen in 2007 in the southern hemisphere, but it will happen. We will have another spectacular northern comet. So they're beautiful things, intriguing objects which have fascinated mankind for many, many millennia. But of course, scientifically, the basis here is that comets are leftover material from the birth of our solar system 4.6 billion years ago. Effectively, the rubbish left over, the dust, the water in the outer reaches of the solar system, the material that didn't make its way into planetary bodies at that time. But those same bodies may have played a key role later in bringing water to the Earth. The Earth itself was way too hot when it was young, close into the sun, to actually have water on the surface. So asteroids and comets may well be the source of the subsequent delivery of water, but also organic materials. We know that they're rich in carbon-bearing species, but also even in primitive amino acids. We know that at least one comet has glycine on the surface. And so by going to a comet and examining it in situ, not just flying past it, but examining it in great detail, landing on the surface and studying its evolution as it goes around the sun, we can hope to unlock a treasure chest of information about the origin of our solar system and to some extent the origin of ourselves. So it truly is a mission that needs years and years of dedication to get to where we are today, and now we're revealing the great secrets from the comet which we're at. Of course, this mission has a precursor in the European scene, and that's what you see here is Comet Halley in 1986, and this was a flyby by the well-known Giotto mission, part of an international fleet, of course. It wasn't there alone, but Giotto got closest and flew past at 68 kilometers per second in 1986. And the way I think about that is effectively with comets are typically on rather elliptical orbits. And when they're in the inner solar system, accessible to us, they move at high speed. And so what Giotto essentially did was, if you imagine a sprinter, okay, imagine Usain Bolt, and you want to have a chat with Usain Bolt. Well, none of you can run as fast as him, right? Well, I don't think anybody in the room can run as fast as him. So if you want a quick interaction with him, you wait till he's running the 100 meters and you just step in front of him. You won't get very much out of him, but you can be close to Usain Bolt for a small amount of time. So that's what we did. We ran out effectively in front of this comet and had a brief encounter. But if you want to study the comet in detail, you've got to work yourself. You've got to find a way of getting to run alongside Usain Bolt, okay? And that's non-trivial, and that's why it took so long to do what we've done with Rosetta. Of course, there have been other comet missions in the meantime, flybys, all of them, and I just chose one here. This is Comet Tempel 1, which was encountered by the Deep Impact mission. This is shortly before the impactor probe hit the surface and revealed material from underneath, which was then imaged by the second part of the mission. And this was our prototypical picture of a comet at that point, a rather potato-shaped object, rather smooth object, and therefore somewhat trivial to land on, you might think. We now know better. Of course, Rosetta started in the early 1990s as under construction, and then towards the end here, in around 2000, 2002, you get a sense of the scale of Rosetta, because Rosetta is the spacecraft that's gone furthest in the solar system on solar panels alone, on solar power. It has a wingspan of 32 meters, special low-temperature, low-intensity solar panels, which you can see here developed for Rosetta. And you see Rosetta, the box, roughly a 2.5-meter cube. You see there, you see in a little more detail here. Rosetta, of course, carries all the main science instruments, the big science instruments internally and on its surface. And then you see Philae, which Bernd will talk about after me, perched on the side there, carrying its own science instrument complement. Roughly half of the mass of the spacecraft, Rosetta, is fuel. And so by now, Rosetta has actually lost roughly 1.5 tons in getting to where it is. That's a very bad way of looking at slimming if you think about it. You lose a lot of weight, but you don't change your size at all. That's not the idea. But of course, in 2003, we were ready for launch, but there was an Ariane 5 failure at that point, not Rosetta itself, but caused Rosetta to be postponed for a full year, and therefore couldn't go to its original target comet, Comet Virtanen. But in 2004, the launch occurred towards Comet 67P Churyumov-Gerasimenko. And so here is the launch in 2004 on an Ariane 5 from Kourou. And of course, despite the enormous power from the Ariane 5, it couldn't deliver the required delta V to get to where we wanted to go, because we wanted to get onto an elliptical orbit with a comet which goes out as far as Jupiter and comes in as far as between the orbit of Earth and Mars, 67P. And in order to do that, to get onto that orbit, to not just fly past the comet, but have an encounter, as we've heard from Dawn, Rosetta did this as well, used gravitational flybys of the Earth 3 times, once a year after launch, as you'll see here, and then twice more. One flyby of Mars. The Earth gravity assists were effectively to speed us up, but the Mars flyby slowed us down but took us into a more eccentric orbit. On the way, we were able to have encounters with 2 asteroids, asteroid Steins and asteroid Lutetia, as we transited the asteroid belt those 2 times. But of course, this was all winding up to the encounter which happened last year, so an awful lot of time was taken in order to get out onto the orbit. In fact, so much so that the comet itself, you can see here, enters the inner solar system, but we're not chasing it for that encounter, but for 6.5 years later. Most crucial phase was as we flew past Lutetia here and then went on towards the comet. Even though we had these large solar panels, we didn't have quite enough power on board to run all of the systems safely. So the decision was made, and it's one that I know that Paolo and his team sitting in the audience here deeply regret at the time, was actually turning the spacecraft off, or at least most of it, and putting it into a stabilizing spin so that the solar panels would remain oriented towards the sun, and then waiting for an alarm clock to go off on January the 20th, 2014. In the meantime, just a couple of the pictures which were taken during the voyage out towards the comet. This is my favorite one of the Earth, taken in the 3rd flyby. A picture of Mars, and then something you'll see also in Bernd's talk, the rather 21st century selfie, taking a picture of, it's actually not just a selfie, it's a Shiva camera on Philae taking a picture of Rosetta being photobombed by Mars in the background. So we're right on trend with social media on this mission. The encounter there by Lutetia. Lutetia is a rather large asteroid, 130 kilometers across, and even though this looks very close, it's at 3,000 kilometers. And of course, we've got much closer to the comet in the meantime. On January the 20th, as I said, we had the expectation of wake up with the alarm clock going off. There were very many nervous people. This is actually shortly after the sweepstakes in the room, in the control room at ESOC. There was a sweepstakes amongst all the people that knew the mission better than anybody else in the world. And at roughly 6:30 in the evening, the first time on the sweepstakes went past, and everybody went, "Hey, you didn't win." And then 2 minutes later, "Oh, you didn't win." And then the last person went past, and that's when everybody got quite nervous. So this is Paolo Ferri here, Director of Mission Operations in Darmstadt, and Andrea Akamatsu, the Flight Director on Rosetta. Also in the background, you can see Emily Baldwin, who is our social media guru. She is the voice of Rosetta, and whenever you hear Rosetta saying something, it's actually Emily. I hate to say, we didn't actually install Twitter on board Rosetta. We weren't quite that far ahead. And of course, the signal did arrive some 18 minutes late from both the ground stations that were listening, and tribute was given to DSN here, and that's something I would do again, that DSN has been very important here, along with our main antenna, 35-meter dish at New Norcia in Australia. And of course, that was the point at which this rather iconic picture was taken. And of course, it's huge relief, because without that wake-up, there was no mission at all. The 20 years that preceded it would have been for nothing. So we were on target for the comet. And just to show that we were approaching a comet, these are pictures taken by the OSIRIS main science camera going towards the comet. You can actually see it had an outburst in April, May last year. So it was indeed a comet, not an asteroid. In fact, perhaps even slightly concerning that it was getting active that early. But after this, the activity died down again. But that's a critical aspect of this whole mission. This is not an asteroid which we can depend on to stay the same. It is a dynamic, constantly changing object. As we approached, the surprises began to mount. This is the famous rubber duck, which everybody's heard about, an interpolated version of this. And at this point, nobody had any idea whether this was actually two objects, a possible contact binary, or whether it was one object eroded. And I would say at this point, the scientists were getting quite excited. They thought they might get two comets for the price of one. On the other hand, the mission operations guys were getting quite nervous because they had to land on this, let alone orbit it. And this is what it started looking like. It's rotating every 12 and a half hours. You get a sense of the scale here. It's roughly 4 kilometers across. And it's a very complicated object indeed. You could see that as early as July. And of course, when we rendezvoused on the 6th of August, things for the scientists got even better, and for ESOC got even worse, because this was the object that we rendezvoused with. So this is an incredibly complicated object with an awful lot of surface structure, remembering that what we were anticipating was something like Temple 1, a rather smooth, uncratered object. And indeed, this comet has not lived in the inner solar system for very long, we believe. Since 1959, when it had an encounter with Jupiter, its perihelion was moved in considerably at that point. So most of the time, it's been further away from the sun. So how it's become this evolved is really still one of the main questions that we have. Of course, we didn't just go there to fly around the comet. We went there with a whole range of scientific instrumentation, and I won't go through them in detail, but we have images across the electromagnetic spectrum. We have instruments that do spectroscopy, if you like, of the dust and gas to understand the composition of the comet, the material flowing away from it, as well as capturing individual particles and studying their properties. We also have plasma experiments on board. And then with the lander, of course, has imaging systems, and Bernd will show you some of the pictures from that as we went down to the surface and from the surface, as well as a whole range of small laboratory experiments which were able to analyze the material from the surface and the close environment of the comet, as well as a drill on board, which was deployed, but we don't believe actually went down into the surface and pulled material back. But Stefan is sitting in the audience here, the lander manager, and he's shaking his head. He's still not quite sure, and we don't really know at this point. We also had a very intriguing experiment on board that linked the two spacecraft called CONCERT, which did tomography through the nucleus with radio waves. And of course, sending the data back to Earth is done by radio waves, but at the same time, we're able to use the slight time delays in those signals to determine the gravitational field of the comet. And one fact we know about the comet very well is that its mass, 10 billion tons, if we compare that with its volume, 21 cubic kilometers, that gives us a density of this comet of 470 kilos per cubic meter. It's less than half the density of water. So for all that it looks like a sculpted rock, something you might find somewhere out in the desert, maybe in Arizona, for example, it is not a rock. It is made of ice and dust. And understanding how this surface structure came to this is something, of course, the scientists are working very hard on. And there are all sorts of astonishing features that we see, things that look like cliffs, things that look like boulders. But on an object like this, you always have to ask yourself, how did objects arrive where they are? Were they sculpted in situ? Did they drop under the very weak gravity? And indeed, the question arises here, where is down on an object like this? It's not obvious. You see these boulders clinging onto the side of the comet, and maybe down is that way for that part of the comet, but maybe down on other parts is different. Of course it is, because it's not a spherical object. There are large areas which are rather smooth on the base of the comet as well, and how this material got there is this dust that's risen up and fallen back down again. But why is it pooled so abundantly in this location? And how did these boulders get there? Did these boulders roll from somewhere else? Did they rise up from the surface and drop back down again? Are they being eroded from above? But then why these boulders? Why not a power spectrum of smaller ones as well? These are questions we don't know the answers to. To put this into scale, the largest boulder you see there, called Cheops, is roughly 25 meters high. And I thought I would do it even more in scale. And I made the following picture. And then I very rapidly realized I could not release it from the European Space Agency, because if I did, you can imagine what the internet would do. And in fact, we've had plenty of conspiracy theories about this comet already, so I didn't want to add with this particular picture. But so it's unattributed, but I can say I did it. So. And of course, we have engaged the amateur community substantially. This is a picture, for example, made by a guy that works in video processing in Sweden, Matthias Malmer. He's not an astronomer, he's not a space scientist. He's taken the public information we have released and generated this astonishing shape model here. And so that level of engagement with the public is something we've been working for very hard as well. Just a couple of pictures here, again, just to remind you. It probably doesn't work so well in the room. I've had to scale things a bit. But let's be clear, everything you've seen so far, I've boosted the contrast of the comet so you can see it in more detail. Comets, in fact, are incredibly dark. Very, very black indeed. This is Enceladus, one of the moons of Saturn, which, because of the ice which coats its surface, has an albedo of roughly 1. The Earth, about 30% or so. Our own moon has an albedo of only 12%, but of course we see it in the night sky as something very bright because of the contrast. It's bright compared to the background. But 67P has an albedo, it's there, I promise you. It has an albedo of only 6%. It is coated with dust on the surface. There is very little surface ice visible at this point because we are not yet at perihelion. It's been covered with the dust from the previous time around, and now we believe the dust should be shed and we will begin to see material underneath that. People asked very early on, show me a color picture. Well, the comet's there, and I'll now turn it into color by just turning the intensity up. It really is that color. It's incredibly gray. But if you play with color filters, you can actually enhance that slightly, and one image that's been released recently from OSIRIS is this one, and you'll see on the right-hand side, as you're looking at it, the left-hand side, that there is a bluish color there in the neck region, which actually we believe is some surface ice just poking through a coating of dust there. And we think this region is being highly eroded, we know. So there are some features beginning to poke through. Regions have been separated out geographically. We've done mapping of the whole object in terms of its gravitational potential. You would have thought the gravity would be strongest at the heads, of the head and the body, because that's where the most mass is. But don't forget it's rotating. So centrifugal force actually reduces the gravity there. It's not the place with the strongest gravity. And you can also see there are areas on the surface where the slope is quite different to the local vertical, if you like, in the sense you might stand on something and really, in different areas, depending on where you're standing, gravity will be pointing at very different angles relative to your feet. And this is my favorite picture taken so far from close up, seeing this enormous range of, let's call them geological structures. And just to give you a sense of scale, that cliff there is 100 meters high. And so, as I say to most audiences, the first thing you think of course, is base jumping. You would want to stand at the top of that and leap off it. Well, you could, but it would be the most boring base jump ever because it would take you 20 minutes to get to the bottom. And you would arrive at 0.2 meters per second. You would walk off the bottom. Your parachute wouldn't work anyway, so that's okay. But you have to be very careful because usually with base jumping, you actually start by pushing up and out. But if you pushed up at 0.9 meters per second, you would reach escape velocity. And that's the equivalent. I won't make you do it today. I do it and take a picture, but you should all jump 4 centimeters off the ground. If you can jump 4 centimeters, you can jump off this comet, okay? It's quite easy to reach escape velocity. But of course, the comet's becoming active, and that's the important thing. We're trying to see it as it gets closer to the sun now and trying to understand how it's going to evolve over the coming months as we approach perihelion in August and go beyond. And so you see material flowing away from the neck here. We see that in certain craters, material, and these are not craters created by impacts from above, but they're material which is, if you like, sublimated and captured in gas pockets underneath and then exploded outwards. There are very few actual impact craters on the surface of 67P. But if we increase the contrast, we can see material beginning to jet out here. We've captured dust particles, and we see that the particles we capture at the moment are very, very fluffy. They fall apart as soon as we capture them on board Rosetta. And we believe this is dust from the previous round, the previous encounter, which is actually in orbit around the comet, not dust which is flowing away today. One of the key results that's been obtained so far is looking at the isotopic ratio of water, so looking at normal water, H2O, to deuterated water, HDO, and looking at how that ratio compares to the ratio of light water to heavy water on the Earth. Again, trying to examine this question, did the water on the Earth come from comets? Well, it didn't come from this comet by definition, because this one hasn't hit the Earth. And that's kind of important, because you look at one object and you get one answer. What does that tell you about the entire sample of comets? Turns out 67P has the highest ever ratio measured of deuterated water to normal water. So this kind of comet cannot have created the water on the Earth. It's way higher than the H to D ratio that we see on the Earth. And so going back now to this picture that we're looking at asteroids, a mix of comets perhaps. We know comets must have hit the Earth, but how many? What fraction of them could have actually been involved in the Earth's water? We may get to see something very interesting soon as well, because all we're looking at the moment is material flowing away. But if the comet falls into two pieces, which it could, because there's a 500-meter long crack in the neck of the comet, and we know that comets fall apart. We saw it famously with Shoemaker-Levy 9 when it impacted Jupiter. So that would be a fantastic bonus for the scientists if 67P was to fall apart this year. Of course, Paolo, again, is going to take early retirement if it falls apart, because how they fly around two comets simultaneously is anybody's guess. So Bernd is going to talk to you about landing in detail in a second, but I'm just going to show you, it's the IAF, and the second word astronautical. So I'm going to show you how an astronaut would land on a comet. It's very simple compared to what Bernd's going to show you.
Got it. Admittedly, it's translating really slow, but at least we hit our comet.
So that's Alexander Gerst on the ISS, who did a long demo film for us for educational purposes. And I show that as a joke, of course, but also because we put a lot of effort into outreach and education on this program, and I think we did reach places perhaps that other ESA missions have not reached before. I don't have the time at all to show you all of that, but I'm going to show you just a couple of snapshots, and if anybody wants to see the real films at the end, we actually made a science fiction film about Rosetta, famous ambition. Well, you need to see the film if you haven't seen it, but the idea was to capture an audience that was not the audience in this room today, let's put it that way. And to date, it's had 2.5 million views. It's been very, very influential, to the extent, I'm very happy to say, that NASA came calling and asked us to help them with the Orion crew vehicle outreach campaign. That's pretty cool for ESA. So. And at the children level, although I know that adults love it as well, the famous Rosetta and Philae cartoons. We have roughly 15 minutes worth of films now the adventures. They're all actually scientifically pretty correct, but this idea of anthropomorphizing the spacecraft, which of course our colleagues in Japan have done before and other missions have done, this was extremely successful. But just to finish, just a couple of items, just to give you a sense of the impact. Front cover of Science magazine as Science Breakthrough of the Year for last year. 2 Google Doodles, which were created for landing and then for the end of the year. Just one point here, on the 12th of November during landing day, we knew that Google had made the one you see in the middle there. We'd worked with them for some weeks beforehand, and on the morning we went to Google and looked for it, and it wasn't there. And so I immediately sent an email saying, you know it's today, right? It's not tomorrow. And then the lady wrote back and said, yeah, but we're not putting it up until you've landed. So there was no pressure. A risk-averse corporation right there. And Andrea Komatsu, the flight director, was one of the top 10 people in Nature for the summary of the year. And as a Brit, I can say safely, it's just not often that the UK congratulates Europe on anything. So this was quite a good thing. And just to give you just a couple of short videos, both Google and Facebook talk about, they put a summary video at the end of the year to show the influential things, the things that made highlights, and there's just a couple of those quickly.
The most powerful force on this planet is human cooperation.
Stop defining each other by what we are not, and start defining ourselves by who we are. We can all be freer.
So that's the one from Facebook. The one from Google is slightly weirder.
Did you hear those words?
Just rendezvousing with this comet is an extraordinary thing. We're going to make discoveries that no one's imagined yet.
So to be the closing item in Google's Summary of the Year 2014, I think the impact has been enormous. And Ambition was nominated for a major award in Hollywood as well, so this is all good stuff. Just to finish, of course, we're now past the landing time. Bernd's going to talk to you about what it is that we're waiting for, perhaps sort of wake up, the return of Philae. But we're obviously continuing with Rosetta, and we've been conducting a series of close flybys. This is the closest one ever done at just 6 kilometers above the surface. You can see here on the right-hand side, NavCam, a portion of the base of the comet here, just zooming in. You're seeing this astonishing array of features that have to be explained now by the cometary scientists. How do you get these kinds of craters and cliffs and boulders and smoother areas? And then we zoom in for the last one, which is just the piece seen by Osiris in its closest flyby, and in tribute to Hayabusa, there's the shadow of Rosetta taken at high phase angle. We're not so close you can see the outline, but we're at 6 kilometers or so above the surface there. And of course, we're at a dynamic object. This object is changing every day, so it promises something spectacular towards the middle of this year as we approach perihelion. This is a gallery of images we've released in the last 2 months, showing you from a variety of angles the jets and outflows. It's really building up now, and we're looking forward to a very exciting time. So let me just finish by telling you where we are. Well, again, for me, a lot of this mission is about outreach and education and inspiration, as well as doing the science and doing the engineering. So that's why I choose this picture here. And I think we have reached out well beyond many missions, and I'm very proud of that for the agency. We are in this flyby phase at the moment where we spend little time close to the comet and then go out to larger distances and come back as the activity builds up. Perihelion is August the 13th. The current end of mission, as funded, is the end of this year, but we fully expect, everything else being equal, that we will carry on until late next year. And maybe we'll leave that for the questions, what we might do in September 2016. You have the guy in charge sitting down here, so we'll see where that goes. And again, please follow along with the mission. So thank you very much, and I'll hand over to Bernd.
Thank you, Mark. Fascinating mission as well. Very exciting what's going on with the mission and the way the whole public outreach campaign has been managed. I turn it over now to former IAF President Bernd Feuerbacher, who will give us the other half of the Rosetta presentation.
disappear. Sorry. Yeah. After this exciting presentation and the other two very exciting presentations, I would like to show you how our little and brave comet lander came down on this very odd target that you have just been described by Mark McCockran. I called it brave, and you will see in a minute why. Philae is really designed complementary to the Rosetta orbiter, and it's meant to work on the very surface. So what we do is we look at topography. We have 9 cameras on board, panorama cameras in every side face of this thing. There's a camera, there's double cameras here, there's a camera looking down. So it's quite well equipped with cameras to look around. We do, of course, have instruments to analyze the material right at the spot in situ. We have 2 mass spectrometers, COSAC, which is a time of flight, and it has also gas chromatography. Ptolemy is an ion trap. There's a drill on board and an alpha proton X-ray spectrometer to analyze the composition at the surface. We measure physical and thermal properties in C2. We have sounding in each of the legs. We have sensors and transmitters to sound the subsurface region. We have a penetrator on board, that's this thing here, to hammer itself into the surface. We measure fields, magnetic fields and electric fields, and we have, as Mark has mentioned, an instrument that jointly with the orbiter does microwave tomography through the whole body of the comet. Now, that's the first picture that Philae has taken of the very comet, and you see this strange geometry, which is due to the fact that we are still mounted on the orbiter. And just to show you what that means, we are looking at the back side of the solar panels, and you see this characteristic routing of the cabling here on the back side. And this is our target, which we've been dispatched to short time after. That was 12th of December. And it's a very, very complicated maneuver. And we have Paolo here, one of the masters of doing that. Not very many people in the world are able to do that. Starting with a 10-kilometer orbit, there's a transition orbit to about nearly 30 kilometers, and then a very strange maneuver is initiated. The orbiter is really sent very close to the comet, and then it turns off and sends off Philae to the rotating comet. You see, it's really a very, very complicated way of getting there. That's our target region. It is actually located on the smaller lobe on the head of the duck, and we were targeting for this flat region here, and we actually landed very, very close to it, a real masterpiece of orbital mechanics. This is the descent imaged by the OSIRIS camera, which showed you these beautiful pictures of the comet. And I tell you, when we saw these pictures here, it was really overwhelming for us, because for the first time we could see that it actually stretched out its legs. And you have to imagine it's not only 10 years in space that this thing was traveling, crumpled together. We actually delivered to ESA in October 2001, so it's 13 years that these joints have never been moved, and it actually worked. That was very rewarding. Now, during descent, this down-looking camera, ROLIS, made its first image from about 3 kilometers, and you see the landing area here. You see the smaller lobe of the comet, and you see part of a leg taking during descent. I can show you one picture more here. And all of a sudden, what looked so smooth from the distance, even with the high resolution cameras, now is pretty rough, and there are little pieces hanging around, there are outcrops, there are boulders, and you can see that a close-up really gives you a different view than the distant, even though the distance was only 10 kilometers. Then this fantastic series of images was again taken by the OSIRIS camera. You see actually the lander at various positions during its descent to the surface of the comet. You see the impact of the three legs in the soft surface material. This is after, this is before. Really amazing. And then unfortunately you see it traveling away after its first touchdown, and you can see it here in the shadow. It looks as though OSIRIS, the wide-angle camera of OSIRIS, has actually caught the lander disappearing beyond the horizon. It traveled across this crater-like structure here and crossed the rim, and that's probably where we've seen it for the last time. And we couldn't see it in the meantime, but this is what Philae has seen. Our panoramic cameras, the Shiva cameras, took this first picture here in the location where Philae finally got to a rest. And what you see here is material that is 4.6 billion years old. This here is 25 years old. So it's really an amazing picture, and it's also interesting that we've seen all this dust all over the surface, but here there's no dust. So we're really very close to what we were aiming for, and this is the complete panorama. It's a little bit too light here, but this is the picture I just showed you. There are two more pictures that were in the shadow, but lucky enough, this camera has such a high dynamic range that they could even get the structure out of the shadowed region. Here, the camera looks into deep space, and it sees a little part of the consort antenna. You can see the position that Philae has between these pictures, with the three parts of the legs still being imaged by the cameras. So that's the location where we present are. And there's one camera that actually can look at the very spot under the lander. This is the same camera that took the pictures during the descent, and you see now structure at a resolution of less than a millimeter. And again, it's very different features that are found in this area here. Now, where is Philae? Now, that's a big question. It landed somewhere here, it crossed this depression, it moved over the rim here, and it's probably located in an area here. This is the way that the consort instrument has confined the final location, and it's actually an area of 300 by 30 meters where Philae is now, but we really don't have yet an image and a final position. That's the way we think. It's sitting between rocks, and if you look at one of the pictures of the panorama camera, we can imagine that it's such a piece of a rock that it can see on the side, and other cameras like this one here are looking into deep space. So what did Philae actually do? After descent, I show you here the complete timeline. 64 hours is the operating time. That is what we planned to bring along in energy from Rosetta with batteries. And what you can see here is that during all contact slots, that's the blue regions here, we had very good communication between Philae, the orbiter, and the ground. All instruments received data, not all data fully satisfactory, but they received data. And during this separation, descent, and landing sequence, which is this part here down to the first touchdown, everything worked exactly as it was pre-programmed. Then Philae touchdown. The touchdown signal was given to the main computer, and this started the initial pre-programmed science sequence, which now happened as planned for a sitting lander with the harpoons fired, but unfortunately, as you might know, this did not happen, so the lander took off again, and it made a 2 hours jump to another position. During this time, some of the science could be, the procedure that was run was meant for sitting down there, so it's not really what we wanted to have, but we got some very interesting data for the mass spectrometers right on impact. Then we realized there's something different from the planned landing. Reprogramming was necessary on the ground. During that time, the lander was in safe mode. That is, instruments were running as far as there were no moving parts involved. So, for example, the mass spectrometers were operated in their sniffing modes. And then there was, during this time, a new timeline was developed, and it was sent up to Philae, which followed all the commands. The hammering device and the alpha proton X-ray spectrometer were deployed. The drill was activated. Amalia is sitting here. It was operating wonderfully, extending fully, coming back again, but it probably didn't hit part of the surface. It was a little bit too far away. I showed you some images from ROLIS, from the down-looking camera. The sensors in the legs were activated, and the tomography instrument was run in various modes. Just to summarize up what we have already achieved, you saw the panorama pictures of the Shiva camera, which is the first real close view of a material that is as old as our planetary system. The magnetometer had some very interesting data. Here, it's a very sensitive instrument. Here you can see the impact measured on the magnetometer. It's on a little arm that moves down at the impact, and you can see that here. You can see that there were 2 bounces in between. You can also see that very nicely from the magnetic measurements. But the interesting thing is that this instrument actually profited from the fact that Philae didn't land in a single place, but in several, because it could make measurements, magnetic measurements, at different places on the surface, and therefore confirm that there is quite some limitations to a theories on comet formation and planetary formation from the magnetic point of view. The down-looking camera I showed you gave pictures during the descent, and it did pictures on the final site where it's sitting now on very short distance. The seismic sensors, Sesame, have, for example, seen the bounce on the first touchdown. This is on the 3 different legs. You see, you can easily identify the leg which first touched down. And it also observed other instruments, for example, the hammering device. You can see the hammer beat here on various legs, and you can see every single of those. So that also gives us interesting information. Concert acquired data for a whole revolution of the comet. Unfortunately, to do the detailed analysis of the interior structure, we need a much more accurate position of the lander on the surface. So we're really waiting for an optical identification that might help us. Ptolemy and Cossack analyzed the material of the comet in situ, mainly from the first impact. They got a lot of material in there. They analyzed it. Unfortunately, together with all the other data, this is still under embargo. The papers have been submitted to science. They're presently in the refereeing process, and I have been asked to be very reluctant to talk about these things. And if you want to identify something for example, glycine, you really want to make sure that before you publish this, you're very, very certain. So they're still working on this, and it's not quite easy because you have to really avoid any double interpretations. Now, Philae is now asleep. When the batteries were exhausted, it went automatically into a dormant mode. The energy level increases as we approach the sun. We have about 1 hour, 20 minutes illumination every 12 and a half hours. And this is not very much energy we get, and all the energy that Philae presently receives is fed into heating of the instruments. And once it has reached 45 degrees, then the energy, minus 45 degrees, sorry, the energy will be then fed into running up, into booting the lander, and we need about 6 watt for this. This could have happened, so we did make some contact attempts in about 11 rotation periods from 13 to 20 March. We did not get any response. We have an instrument that was produced in Ireland by Susan, sitting up on the orbiter that ensures the communication. Everything works nice, but we would not expect an answer yet, because to boot up you need about 5 watts, which we could possibly have now, but to send the command, yes, I understood you, we need nearly 20 watts, and this is not yet possible at the present time. So we try again in April for another period when we have suitable conditions with the orbits. I don't expect a real communication before June, July. That's probably the earliest that we could have success. There's a search opportunity for an optical location, possibly on April 25th. And what I can tell you, we need some patience for the wake up, but the chances are good. So let me conclude. Philae has achieved the first ever landing on the comet core. It came down not only once, but 3 times altogether, and it made a lot of scientific measurements there. It has coped with unexpected situations and achieved most of its objectives, which admittedly have been very, very ambitious. The in situ observations of Philae really complement the Rosetta data, and there's a strong interaction between the scientists on the orbiter and on the lander. the early results that I showed you part of that are presently in the publication period enhance our knowledge of comets and planetary evolution. And finally, my congratulations to the teams of ESA and Philae and to the operation teams in Darmstadt, which did incredible jobs. Be patient, there will be more. Thank you very much.
Thank you, Bernd, for that presentation. Certainly, congratulations are in order to the entire team on that mission, and we'll watch with excitement as we go through the next few months. So we only have a few minutes left, about 10 minutes, is that about right? Okay, so we'll have a few brief questions. If anyone has any, just write them on a piece of paper perhaps and pass them up. I'll perhaps prime the discussion with a question for the full panel. We've seen on all of these missions the impact of communication, public outreach. On the Dawn mission, certainly there's been a lot of interest in that mission over the last couple of years. Hayabusa has gathered a lot of interest, certainly in this community, but more broadly. And then the Rosetta mission has been phenomenal in its impact internationally. So the question for all the panelists is, to what extent is this outreach and public engagement planned into the actual design of the mission and the design of the operations? And to what extent is that a lucky byproduct? And are there lessons to be learned from that that can be shared? So I think the microphones are live on the tables, are they? Yeah. So.
I'm not sure if this is on. Is this on? Okay. Well, planned in the sense that, yes, of course, I mean, even 20 years ago, it was foreseen in the science management plan for Rosetta that there would be communications and outreach. But of course, I remember reading one of the original documents for OSIRIS, the camera there, in which it talked in sort of weirdly hushed terms about this thing called the World Wide Web. And that images would be released on the World Wide Web. And because it was 1992, 1993, and then even later on, things hadn't developed fully. So to say that there was a communications plan, yes, in a broad sense, but in specific terms, it was developed in the last 18 months or so, the last 2 years. There were many things that we did with Rosetta which I think were new for ESA. One of the things which we've engaged in, and others have done it as well, is blogging, for example. Routine access to to information, to images. Many of the images you've seen, we release 3 images a week. We get stuff out there. But of course, once you invite people into your living room and ask them to sit down and have dinner with you, you'd better provide dinner. You can't come along with a few salted crackers. I hope it's better than that in the reception, by the way. But the point is that if you open the doors to people and say, we want to engage with you, we want you. My dream of the whole mission was to have people stand around whatever passes in each culture for a water cooler, coffee, a place in the morning where you sit down. And I wanted people to talk about their comet and their mission, not ours, but theirs. I mean, after all, they paid for it, but I wanted them to take ownership of it. But of course, when people take ownership of things of it, they have expectations about what you should be doing for them. And there are lots of lessons we've been learning about how once you get the public in the room, you'd better deliver and you'd better be responsive to the public and you better expect a fraction of the public not to be happy with you, whatever you do. I have many sleepless nights notched on my bed, waking up at 3 o'clock in the morning thinking, how do I answer that question? That's not something I can answer, or it's not something I should answer. So I think it's opened a new door for us in the way that we interact. But I actually think very broadly it's been very successful. And I hope that we can continue doing more of it. I think just as one final thing, I'm not sure if Jean-Jacques is still in the room actually, but when we made Ambition, the film, the science fiction film, we did that almost completely secretly inside the agency, partly because we wanted to release it so that people didn't know what the film was about. We wanted a kind of a viral, what's this thing, what's this film that people are seeing. I will admit, in between these four walls, I was slightly nervous that if we told people what we were doing, somebody somewhere in Paris would say, nope, you're not doing that. We got away with it, okay. It worked out very well, and hopefully we can do more of it. I hope people don't turn around and say, we're not doing that again. That was science fiction, what's that? Anyway, I'll pass to my co-panelists.
As for the Hayabusa 1 mission, end of the Hayabusa 1 mission, Japanese movie maker developed the 3 or 4 movies, and that is the unexpected phenomena. So this is not the planned operation. So that's another phenomena. So as for the our side, at the Firaya landing campaign, so ESA and the DLR has a good information generate. So we should run so much. So that using the live space operation. So if we announce these live data, so we can make a consensus to get the affirmative national consensus. So that I learned from the Firaya landing campaign. So as for the Hayabusa 2 mission, we want to take the intensive outreach to make a consensus in Japan.
Okay, talking for Philae, I mean, let's be honest, we were amateurs. We didn't plan any public relations or any communication right from the beginning. On the other hand, going to a comet, landing on a comet, is something that you can communicate to people very easy. They understand why and what's so interesting about comets. And this, of course, we did very, very thoroughly. But we were really very impressed by the public work that ESA has done. They did a fantastic job. I've never followed a mission that had so much contact with the public through Facebook, through Twitter, through TV shows, newspapers, and it was received very well. And even when Philae had this jump and the harpoons didn't work, there were no negative comments in the press, things that usually the press just jumps on because they look for failures. But here, the positive sides were really seen, and we were really very impressed and very pleased. And I would like to thank very much to ESA for this great work that they've done on the publication, on the communication in this area.
Well, I can say that for Dawn, it was conceived in an era before there was the internet just about. It was back in the late 90s and early 2000s. So engagement was not a fundamental part of the overall mission design. It was an important part of the proposal, but not necessarily a mission design objective. I think what you've heard is that all of the space agencies have adjusted. As new capabilities have come aboard and been available to us, we've mutated, we've changed our way of going about and actually approaching the public. And I think we've had to. I think we all owe a great obligation to the people that fund these missions to make it exciting and to bring forward the knowledge in a way that they can understand it. And I think that the organizations that you're hearing are in fact doing that and doing it successfully.
Thank you. I think that last point is quite important. We're, I think, at a point in space where we really can't afford to be amateurs in this anymore. And we work in such an exciting field. We often take it for granted, but we really need to communicate that to the outside world. And so we don't all need to be communications professionals, but having members of the team that can transfer that excitement and that interesting development that we're doing to the public, I think is very important for reasons of support and funding, but even more importantly because, as you said, those missions are for all of humanity, and that needs to be communicated out. I didn't get any questions sent up. I'll ask one more. We are a little bit short on time because it was hard to fit in all those exciting presentations in the short time we had. If you do think of a question later, I'm sure the panelists will all be at the reception after, so please take advantage to ask your individual questions. I'll ask just one last question to the panelists, some or all who would feel to respond. We've seen a number of things where new things have been learned in the mission. Jim, you talked about the way ion propulsion actually, you had to think about missions differently. Other lessons learned that have come up also on the other missions. To what extent are those documented or shared between agencies? Is there collaboration that goes into the planning of these missions as well?
I'll start just very briefly. I don't believe there's a lot of collaboration that goes into the mission design. I think it's done by the teams that come from the different organizations. However, it's forums like this in which we exchange the information, and that gets taken back to those entities and to those individuals that are thinking about future missions. And I think that's really how we exchange the information and make sure that it gets fertilized, you might say, in other minds.
I mean, scientists are always very, very much communicating all over the world. Science is a global family. And one example is, landing on a comet is a relatively rare occasion. So you cannot just pass it on to others. But we have Stefan sitting here, and he is the investigator on the mascot lander in Hayabusa. So there's a very close link. It is just transferring the knowledge from one mission to the other, and we hope for other missions coming up where we can also make use of this unique experience that we've gained.
So as for the JAXA, so in the historical meaning, we have a tight collaboration with NASA. So that as for the Hayabusa 1 on another deep space mission, we were supported by NASA. And then in that sense, as for the result of the Hayabusa 1 data, so we have a chance to share with NASA. And so we are now discussing about that topics. And as for the Hayabusa 2, we have a good collaboration with the DLR, and so that we want to expand this relationship to the future missions.
Yeah, just to loop back to one of the points made earlier on, I mean, this business of why it was that on landing day, for example, that the world didn't go ballistic when we bounced. I think there's a lot to be learned in that sense about expectation management, and we learned an awful lot actually from NASA's Curiosity mission in that regard. So in that sense, in the outreach sense, there's certainly lots of lessons to be learned. But I think as a mission, I'd agree with the other panelists that this carries on largely at the scientific level between the instruments. Of course, we have the agencies who are taking part internally within ESA, and then in this mission as well, also on Philae, they're separately, so to speak, with DLR and CNES and ARSI. So there's a constant interchange there, I think, between the various partners and the US as well. I mean, a key partner in the mission. But one of the interesting issues for me is that you would want to go out and fly another Comet mission tomorrow, right? Or you should have been building one for the last 10 years with those lessons learned. And having a mission cadence which actually learns internally with an agency is something which I think we probably struggle for. I mean, I am certainly envious of JAXA in this regard. They went from Hayabusa 1 to Hayabusa 2. Rosetta 2? When's that? Okay. I mean, and it's taken so long to even get to Rosetta 1. We should have been started Rosetta 2 years ago. And we have that across the whole space agency. There are lessons we're learning with technology which we don't necessarily get to apply them until much later on, and then people in the agencies retire, that knowledge is lost. I think it's critical that we have a more thorough lessons learned, lessons documented. But of course, even then, as we said about the internet, technology changes. You can't necessarily learn, they're not necessarily applicable 30 years later. Certain things, yes, certain things are fundamental. But I mean, we certainly would be looking forward to, we're flying a big mission with an ion engine, Bepi Colombo. And that's going to be driving downhill towards Mercury for a long time, and anything that might have been learned in along the way kind of stuff. Well, we've built the mission now, we're ready to go, but we should certainly be talking to NASA about that. And there are many things we could learn if we have an asteroid sample return mission of our own at some point. There's OSIRIS-REx, other people have proposed that in Europe. There should be discussions there.
Thank you. Thank you. Mark, your last words there, I think, underline perhaps even a little bit the benefit of this exchange of information, and really each agency can't do everything. As you said, you can't have Rosetta 1, 2, 3 going, but we're all part of this perhaps global family in space, and to the extent we can exchange those lessons and move forward, we can share in the successes all together. And I think, as Jim said right at the beginning, the IAF really is a wonderful forum for that. When you think about it, for over half a century, the IAF has been bringing the global space community together. And world politics have gone through some pretty dramatic changes during that time, and yet we have a neutral ground here where those ideas can be exchanged, and where we as a global space community can move forward together. So with that, let me thank the panelists for sharing these very interesting missions with us. I also would like to call upon the IAF president to say a few closing remarks, please.
Thank you, Chris. As IAF president, I'm very honored to provide this exciting opportunity, and we are really enjoying to sharing these exciting results, and also the discussion on how to cooperate, expand our cooperation. I already observed some kind of operation about the computer between the ESA and JAXA. I'm really happy to observe that thing. Anyway, I'm a little tired, but wasn't that exciting? Let me tell you a little bit about why. I would like first to express my sincere appreciation to all, especially Dr. Salberger as the moderator, and the 4 excellent speakers, Dr. Graf, Kuninaka, Feuerbacher, and Makorian, for being here to make this event so impressive. We all agree that the space activities bring us dream, hope, and also a lot of the inspiration. On the other hand, it is true that the space activity require great costs. The recent trend, therefore, attack importance to how useful space is for us. All space agencies face the challenge of explaining the cost-benefit of our activities. However, Dawn, Rosetta, Hayabusa, these 3 projects are the exception. They, without any explanation, we need a little bit explanation. Satisfy the security, curiosity, supply the inspiration, and give interest and yearning, especially us who are engaged in space development, are impressed by these 3 missions because they prove the excellence of the long-term space activities. Why? If the exploration to Mars or Venus is the main road, exploration to small asteroid is the Columbus's egg. The spirit of the science who planned these missions sees our heart and inspire us toward more innovative ideas. There is every possibility of innovation in space field. Today, I was fascinated as I listened to these sessions, feeling like a boy when I started to aim to be a space engineer. We love space exploration. So thank you very much again, all of you.